Hi everyone, Mr. Ford here. Today we're going to talk about how to draw ray diagrams for thin lenses, the two types that we discussed in a prior lesson. So these notes that I'm going to talk through are posted on Schoology within the optics or light unit, and also they're going to be in today's lesson folder. And then we're going to jump into two problems in the packet. Page 14, this is where we're going to kind of merge my traditional packets with MacPacks. So here we go. So just to explain a couple of things, the universal kind of object in physics is a candle, right? Because if we were in class, we would use candles for our lens labs to show the light going through in a dark room. The other thing to note, this is our lens. In some ray diagrams, you may have a light ray that goes above that lens. So that's just because the pictures that usually we have are not big enough to go up there. Just know that we would imagine that this lens here would extend all the way up as big as we needed it. Another thing you'll note, so this is our lens axis that I just drew. Then we're gonna have our other axis. This is like the bottom of our object. So that's kind of like our other horizontal axis that we're going to look at. So if things are flipped on this side, they're going to be upside down usually. And on most ray diagrams, at least for this class, you'll have some dots. Sometimes you'll have two dots. These are usually, the first dot you're going to see is going to be the focal point. So for this type of lens that we have now, it's a converging lens, a convex lens. That means it would converge all the light. So if you had a bunch of light rays coming in horizontally, they would all converge at that location. Nothing big to note for that right now, though. But what we are going to have to do in a lot of our activities today and for the rest of, I guess, like another week or so, right? Because you guys are done, is to scale them. So since we don't have all the same pieces of paper, if you print it out, it might be different sizes than everybody else. If it tells you in the problem that it is a 2 centimeter focal length, it's going to say that this first dot we're going to assume is 2 centimeters. So then if there was another dot, say here, this would be 4 centimeters. So on our packet, which I'll note again, every dot is going to be a certain length. So no need to break out a ruler if you don't want to, but we can estimate. So if we knew an object was at 3 centimeters, we know approximately it's going to be right here. And a lot of times we can replace candles with arrows, especially for people that can't draw them like myself. And with this scale, if we said that the object were about 2 centimeters high, you can estimate this distance and draw something like this. That's not too hard to believe that that's about 2 centimeters. And the same thing for 3 or 1 or anything like that. What we're looking to do is just trace the basic rays that come off of them. So there's going to be 3 rays that we need to draw. The first of which, is going to be going from parallel. So there's going to be a ray that goes parallel. See, this line is drawn parallel to our axis, and then it goes through the focal point on the other side. So our first ray that we're going to draw is called parallel to focal. Our next ray is going to be focal to parallel. So we're going to go through the focal point that's already on our ray diagram on the same side. Once that ray hits our vertical axis or our lens, it's then going to go out parallel to our surface. And you can see that they're already starting to intersect here. So technically you do only need 2 rays, but just for accuracy, we're going to do 3 rays. And then our last ray that we're going to draw is through the center of our lens. And then we would see all 3 of those rays converge here. So that means our object is going to be right here. And we could see that it's inverted. So this is why, even for your eyeball, the image that is on the back of your eye is flipped upside down. If you've ever used pinhole cameras in middle school, the image is flipped upside down. So again, the thing to focus on is our 3 rays. You're going to draw 3 rays. You're going to draw parallel to your horizontal surface, to the focal point on the opposite side. Then you're going to draw through the focal point on the same side, and then parallel, and then through the center. So let's go to our practice. It's going to be, we're going to have to skip a couple pages. So once you start seeing like the MacPack things with the, so this is where we last finished. The mirrors, we're not going to do mirrors yet because they're a little bit more complex. So we're going to focus on the lenses. So this is page 14, lens practice problem number 1. So again, very similar to what we just saw. Keep in mind the scaling. So if this is saying our focal length is 2 centimeters, this is going to be 2 centimeters here. This is going to be 4 centimeters, and the same on the other side. I tend to stay on the left-hand side when I draw things. Feel free to draw things on the right-hand side as far as the object go, because it says we have a 1 centimeter tall object placed 5 centimeters in front of a convex lens. So the lenses are the same on both sides, so you can pick what you want it to be as the front. So 5 centimeters is going to be a little bit past 4 centimeters. So something right around here. And it's 1 centimeter tall, so it's about like half of that mark. So I'm just going to estimate here. I do have kind of a scaling device in front of me. So that's my 1 centimeter tall object 5 centimeters away. So our 3 lenses we're going to draw focal to parallel. I'm sorry, parallel to focal. So parallel to my lens, once I hit my lens, parallel to my surface, sorry. Then I'm going to go through the focal point. So that's the direction that the light's going to go through. So a couple things to note. Straight edges are good. So that's a way you can draw the most accurate parallel line. Mine is okay to my normal horizontal axis. And also making sure that if it's going through the focal point, that it's actually hitting that mark. So line it up the best you can. Now, in the situation we're in now, we're not really going to be measuring, but we want our things to be as close to reality as possible. So that was parallel to focal. The next one, we're going to have focal to parallel. So I'm going to go through the focal point on the same side. When I hit my lens, it's then going to go parallel, the best that I can. And then I'm going to go through the center of my lens. And you can see all 3 of those rays pretty much converge right here. I'm actually going to redraw one of those because it's not actually lining up. So you can see this is close to 4 centimeters. And knowing what the answer is, I could see that some of my rays are not perfectly aligned. Mainly this one. So let's get rid of that little guy. Oh. There you go. So my parallel was not perfectly parallel. Good enough. So you can see what I meant by trying to draw things as accurate as possible. So we'll say right here is where they all converge. So this is going to be my image. So my object was in blue. Again, my object is just an arrow. So my image is in red. That's where those rays actually converge. And that's where I would see my image of whatever I'm projecting. So those are our 3 rays for our ray diagrams. As far as matching our measurements with some equations, That's what we're going to jump into next. So if we were in school, you might hear Mr. Mackman next door all of a sudden saying, "If I do, I die," and "Hi ho, dido." So that's a really fun way to remember the equations. So the one is if I do, I die. Meaning for the inverse of the focal length equals the inverse of the object distance plus the inverse of the image distance. So this is how we would calculate these things. So we're going to fill out this chart over here. So the F for focal length, we already knew what that was. That was given to us. So 1/2 centimeters. Object distance we were given. That was 5 centimeters in front. And the image distance is what we were looking to calculate. So there's two ways to do it. We could actually measure this distance if we wanted to. And we can see that's a little bit more than 3 centimeters. So we plug that into our calculator, and we would get an image distance of 3.33 centimeters, which you can start to see why I redrew that one ray to show that this distance right here to here is about 3.33 centimeters. So the next part is to find the image height, which the equation is m, which I'll get to in a second. So hi ho, dido, kind of like the Disney song. Notice the equation, the equal marks. There's two equations in one here. So we're going to use this to get the magnification. Some lenses make things smaller, some things the same, sometimes bigger. So the magnification would be a factor. So if you get a magnification factor of 3, that means the image is going to be 3 times bigger than what the actual object is. So we'll save that for now, for a second. But we do not know our image height. We know our object height because we were given that. That was 1 centimeter. The image distance we calculated, and in a lab type setting we would measure. And we were given the object distance, which was 5 centimeters. So what we could do is we could solve, if we're using just this part here, we could solve for the image height. So if you plug that into a calculator, it will spit out 0.67 centimeters, which we can kind of see that in our ray diagram, that the red, I kind of didn't draw it the best, but is a little bit smaller than the blue. Notice that my arrow here is a little bit above where the green actually intersects. So that's how we got our image height. Now to get the magnification. So there's two ways to get the magnification. You can use the image distance and object distance, or you can use the image height and object height. It's just a ratio. So since we didn't have in the beginning an image height, why not just use the image and object distances and plug them in? This is another way that you can check to see if you have the right answer. But just because we have our 1 centimeter object height, it is going to be the same. That's just kind of a coincidence for the magnification. Now for the other ones, virtual versus real. Now if you remember us talking about mirrors, when you see your image in a mirror, that is a virtual image. You cannot actually touch that image. So if you stand 3 feet in front of a mirror, your image is 3 feet behind, you cannot reach your hand into the mirror and touch the image on the other side. So that means it's virtual. Now, something like a projector, if you project an image of, say, a bouquet of flowers on a smartboard or a screen or a wall, can you touch that image? Yes, you can touch the image. Now, it's not saying you can touch the object. It's the image. If you can physically touch the image, then it is considered real, meaning that all of those light rays converge to one point. So if all the light actually converges, it's considered a real image. Now, as far as our image being enlarged, reduced, or the same size, just visually, or if we measured, or just from our calculations, our image height was 0.67, but it started off as our object as being 1, so our image was reduced. And would it be upright or inverted? Definitely inverted, because now the arrow is pointing downward. So that's how we would solve a converging or a convex lens problem. Some things are going to change depending upon the position of our object, whether it's within a focal length, at the focal length, or further than a focal length. But we may or may not have time to get to that next week. So the next type of lens we're going to look at is a diverging lens. This is when the light is going to spread out, otherwise known as a concave lens. So let's go back to our notes. Again, these are on Schoology if you want to look to them. There's our equations. Skipping through. Okay, so just like before, we have our image, we have our focal length. Now, something to note, if we have a diverging lens, will the light ever be focused? No. But we do have a focal length here. And notice it's on the left-hand side. It's on the same side as our image. So this kind of follows some rules for mirrors. Generally speaking, whatever the center of curvature is for that circle or circular path is going to be the focal length. And it's given for these types of lenses, the diverging concave lenses, it's going to be given a negative number just to show that the light is not actually focusing it, and it is on the other side of the lens. So same rules. We're going to draw our parallel to focal. Now you may notice that before we would go down through this focal point, but we're not. So why is this pointing up? Well, it's because we're imagining the light, it's kind of hard to see there, is coming from that focal point. So when we go parallel to focal, we have to start at this focal point and kind of imagine that the light would appear to be coming from there. So then we're going to have our focal to parallel, which this is where it gets a little bit more complex. We're imagining that we're lining this up, that it's going to go through the focal point on the other side. So that's how we would line this up. We would line this up as if it was going straight through here, but then when it hits the lens, it goes out horizontally. And then our last one, which is unchanged, the green line here just goes through the center. Now, if you just focus on the solid lines, you'll notice that those lines, right, here, here, and here, do not converge. They're not supposed to. But it appears that they all come from the same spot behind the lens. So if you trace these rays all the way back, the dotted lines, so if you trace those all the way back and then through the solid green line, it appears that something is forming where all those rays converge right here. And again, it's appearing to come from there. So that's a suggestion that it's going to be a virtual image, a fake image, kind of like a mirror. That's why these are a little bit more difficult. So let's walk through this together. As I scroll up. There we go. Okay. So again, our focal length, this is 2 centimeters. This is 4 centimeters. We have a 1 centimeter tall object, again, placed 3 centimeters in front of a diverging lens, so we're going to be right about here. And do my best to draw a 1 centimeter tall object. Let's see if that was correct. Pretty good. So we are going to draw all our rays. So again, we had parallel. And I'm having difficulty getting exactly parallel just because of the iPad. And it's going to appear to come from back here. So you might not want to draw this just yet. So I'm just doing this to line this up. And I get to cheat a little bit because I can erase partially to make this a dotted line. So again, it's appearing to come from the 2 centimeter mark, but it's going to go hit the lens and scatter upward, or bend or refract upward. Then we have our focal to parallel. I didn't mean to erase that. So again, it's like we are going through the focal point on the left side, but it's not. So it's going to go right about there, and then go parallel-ish. But again, it's like that is coming from back here, and then through the center. And something I'm doing that I didn't know in the beginning, making sure all of your light rays start at the same point, meaning the top of your arrow. I did not necessarily do that. But if we zoom in, it appears that they all focus or converge right there. So that means that's where our image would likely be. And it's going to be virtual because the light's actually not converging there. It appears to converge there. And we can see that it is going to be smaller. It's right side up. So let's go through all the calculations. So again, if I do, I die. It's a -2 centimeter focal length. And it's negative because it's on the same side as the image and not actually focusing the light. The object distance was 3 centimeters. Oops. And we're solving for the image distance. So we plug that into a calculator, and we would get a -1.2 centimeters, which is right. It's negative. It's on the left-hand side. And we can see that's roughly 1.2. Then as far as heights, magnification equals hi-ho dido. And then again, depending upon what you have, we don't have the image height because we can't measure it. Object height we know is 1 centimeter tall. The image distance we just calculated. Let's see, oops. Dido. So our object distance was 3 centimeters. So we can plug this to get our magnification if we wanted, which would be not what is on the MacPack. These answers are wrong. Typos there. So the magnification would be 0.4 times, right? And you feel free to put that negative in there to show it's smaller, but I don't think you really need to because it is 0.4. Then we can solve for our image height, image height. Plug that into our calculator, and we get, again, because it's a 1 centimeter tall object, just a coincidence because it's a 0.4 centimeters. And this is going to be a virtual image because the light actually does not converge. It is going to be reduced, and it is upright. And that's what we have as far as today goes. Feel free to review this if you need to. There's going to be a short Schoology quiz for you to complete as well today. So have a nice day.